Hello, everyone. Welcome. Thank you so much for joining us today. We're glad to have you all. As we let everyone trickle in, we'll just do a quick introduction and then we'll jump right in. My name's Kayla. I'm here representing the Acelab team, and we have Denali here from RAiNA. He'll be guiding us through the presentation. Before we start, I want to make sure that everybody knows that today is an AIA-approved presentation. So you'll get credit for the webinar today. If you're worried we didn't get your AIA number upon registration, you can fill out the form that I'm going to be dropping in the chat. That will make sure that we have your number and that you get credit for the session today. We will also be doing Q&A. Towards the end, we'll get to as many questions as we can. However, if you want to leave any questions throughout the presentation, you can use that Q&A button at the bottom of your screen. Drop any questions there throughout the presentation, and we'll get to them at the end. Lastly, we will be doing a post-webinar survey, so we really appreciate any feedback that you have for us. You can fill that out, and we greatly appreciate it. So that is everything from my end. Denali, I'll go ahead and pass it back to you to get us started.
Awesome. Thank you, Kayla. Thanks everyone for joining us here. This is going to be hopefully less than an hour, so we'll have a few minutes left for questions at the end. This is just kind of an introduction, sort of a 101 level presentation about Rainscreen walls. We're going to talk about kind of how they work, different rainwater control strategies, and so on. So I won't read the AIA slide. Kayla already went over that. You will get credit for this. Let's jump right into the learning objectives. So we're going to go over what the building enclosure is, what its main functions are, and then what a rain screen is and how it fits into that enclosure. And then we're going to list why rain screens are good, the benefits of rain screens, how they support high performance design, and talk about the fundamental components of what makes a rain screen wall. Okay, so the building enclosure is really it's the environmental separator. So it's this kind of red line that you see here on a house, but you could draw this around any building. It's really what defines, what's inside versus what's outside. So that consists of the basement floor system, foundation walls, above grade walls, windows and doors, roofs, skylights. Um, we're really going to be focusing today on the above grade wall systems, but the enclosure encapsulates what I like to think of as all six sides of the box. If you imagine a house as a box or any building really. So it's what keeps us indoors instead of outdoors. So um, yeah, so it comes in many different forms. It's what separates conditioned space from unconditioned space, and so we do that by managing environmental loads. And so that's in the form of water. That's the big one. We're going to talk mostly about that today, but also airflow, heat flow, vapor flow, so diffusion. It also manages light, solar radiation, and other things as well that we won't really get too much into today, like noise, fire, smoke, all those things as well. So those are kind of all the environmental loads that we want the enclosure to deal with in one way or another. And also it has to transfer loads. So things like wind loads or seismic or dead loads of the cladding itself have to be transferred through the building enclosure to the main structure. So it has to be strong enough to handle those loads. And then it also needs to be durable and maintainable. Has to last a long time. It has to be economical to construct and maintain. And it has to meet the aesthetic expectations of whoever's occupying and living around the building. So we want to make it look good as well. So we're asking a lot of the enclosure. It's a big focus of any building design. So it's doing all those things all the time for the life of the building. Um, So why do we want to manage water? Why do we care so much about that? Hopefully it's somewhat obvious, but water tends to be the number one damage function for buildings. If you look at data from insurance claims and litigation around construction, the vast majority of it has something to do with water. This is it's a big deal, right? And so we've probably all seen gruesome horror story pictures. Just have a few on this slide here. We don't need to go through all of them. But just some examples of water problems. So water, we have water intrusion, water gets in, couldn't effectively drain or dry out. Thus, it's going to result in damage over time. So this is what we want to avoid. And it can impact all sorts of parts of the building performance. So we want to have this balance, right? So our buildings are going to get wet. That's just inevitable. And so we want to make sure we have this adequate balance of wetting and drying. Walls are going to get wet. They're exposed to rain. How can they handle that water, right? That's what we want to focus on, and that's what rain screens really help us do is balance that wetting versus drying. So there's a lot of examples of bad failures due to water leakage, water intrusion throughout North America and the world, frankly, but we'll focus on North America. You start to see language creep into building codes around water management. Things like flashings and drainage are mentioned. There isn't an explicit requirement for rain screens yet, but we're starting to see more demand for these high performance buildings, right? Durable, resilient, energy efficient. These are all elements of high performance design. And this is where rain screens really come in and shine. So the benefits of a rain screen wall is there's many of them, right? And I would say the biggest one is just really durability. So we're increasing the longevity of the structure and the enclosure components. We're avoiding premature replacement or excessive maintenance. We're reducing costs for owners by managing that water effectively. It's going to make a more durable, longer lasting building. Resiliency is another one we're starting to hear a lot in the face of environmental changes. Climate change is happening. We're seeing it. We're seeing increased wind and rain loads in a lot of areas. And we're designing buildings for not just this climate we're in now, but future climates as well. These buildings have to last a long time, and we want them to hold up to more extreme weather. Um, healthy buildings. This again, rain screens are a part of that just by allowing things to dry out. We're reducing the risk of things like mold growth. This can impact indoor air quality. It can impact people's health, the occupants' health, if we're letting these moisture issues go unchecked. Energy efficiency. This is kind of not directly related to rain screens, but a lot of times if we're adding that rain screen assembly to a building, it gives us an easy opportunity to also add more insulation in that rain screen cavity. So we can adapt existing buildings with rain screen retrofits and add exterior insulation, make them more energy efficient. Safety, this goes hand in hand with that health circle there, right? We're improving the durability. We're getting better wetting and drying management, reduces the risk of potentially structural issues due to unchecked water intrusion problems. And then lastly, just design freedom. The rain screen is not really tied to one particular system or product. It can accommodate all types of buildings, forms, features, building heights, aesthetics. You could put really any kind of cladding you want on a rain screen and make it work. You can fit any sort of design aesthetic here. So how do we successfully manage water? Well, let's talk about what actually causes water intrusion. You need three things. You need water. You need a source of water. So that's pretty easy to get, either rain or runoff, or could be a irrigation system spraying the wall that's next to the building. Some source of water. Usually it's going to be rain, wind-driven rain, hitting the wall. And then the second thing you need is a force. You need a force to drive that water um, through the wall. So that's going to be either wind, could be gravity, could be capillary action. And then the third thing you need is an opening. So you need a hole for the water to get through. So all three of those things have to happen at the same location for water intrusion to occur. And so if you can eliminate any one of those three factors, you can successfully stop water from penetrating the wall. Okay, so there's different approaches to rain control. And I'm talking about either at an assembly level or an individual detail level. You could do this analysis for any one of these. There's really two different approaches. There's either a perfect barrier or imperfect barrier approach. And I don't want to say that perfect barrier means everything's perfect. What that really means is that we're relying on a barrier in that wall to be perfect. It is the only line of defense. This could be like a face sealed system or a concealed barrier where there's a membrane behind something. What this really means is that there's not really an opportunity for drainage or drying. It's really just once that perfect barrier is breached, we don't have any backup. And then the imperfect barrier sort of acknowledges that we aren't going to have perfection in the real world in construction. So we're assuming that there will be some degree of imperfection in construction. So now we want to have our belt and suspenders, so to speak. This is where we get into drained or screen systems. These are rain screen systems, which we'll talk more about. Or the other option is the old school approach, which is just mass or storage systems. Um, so these are just some examples here, right? So perfect barriers, we do actually use these quite a lot in different scenarios. One example is just glazing. So glass is a perfect barrier, right? If the glass is breached, we don't really have a backup behind that. It's just water is going to be in the building. Same thing with a lot of like the old school face sealed EIFS systems, right? It was just relying on that exterior face of the EIFS to hold water out. Once there are cracks or voids in that, then water could get in the building. Um, and then we go into imperfect barrier examples. We've got just big, thick mass walls, right? Old rubble walls, stone walls, think old castles in Europe, that sort of thing. It's the water control approach is really just let it get wet. It will absorb some of the water and then it will release it slowly as it dries out when the rain stops. So it has enough storage capacity that it can handle that. So stone walls, just multi-wide masonry, or we got a composite example here, CMU with a brick facing. And then finally, we get into the drainage systems, right? These are the rain screens. So this could be, siding with a cavity behind it. All sorts of different ways you can do that. And that's what we're going to focus mostly on here. So this is the rain screen wall. Okay, so the definition, which we've come up with a lot of input from industry experts, is this is as simple as we could make this definition. But it's an assembly applied to an exterior wall, which consists of, at minimum, an outer layer, an inner layer, and a cavity between them sufficient for the passive removal of liquid water and water vapor. Okay, so it's a bit of a mouthful. So we'll break down what that means. All right, so we've got some examples here. This is just a really simple wood framed wall with what looks like maybe a fiber cement cladding here. We've got the vertical section or the plan view as well. So it's just got some wood strapping that's holding it away from that wall. So our outer layer is just the cladding. It's the cladding system. This looks like fiber cement. It could be a metal panel, could be lap siding, could be brick, all sorts of things. The inner layer is typically going to be a membrane. So this is the WRB membrane, and quite often also functions as the air control layer as well. We'll get into that later. So that's our outer layer, inner layer, and then we got the airspace in between the cavity. So that's created by these vertical wood furring strips that's holding the cladding away from that inner layer. And then we've got a big enough space there that we can get that passive removal of water. So the liquid water is going to drain out. Water vapor, you'll get enough ventilation behind that cladding that it can get removed as well. Okay, so that's one example, right? There's tons of different other ways to do it, right? You can do it over steel frame, you can do it over concrete, CMU. You can do it with different cladding types. These other examples here show some exterior continuous insulation that's also within the Rainscreen cavity. Um, any sort of building type you can do Rainscreen on. All right, so we'll talk about drainage and ventilation next. So this is where it all comes back to that balance that we were talking about earlier. So there's really four different sources of moisture that hits walls. So number one is going to be precipitation, right? Rain and snow. Could be runoff from above. Um, number two is going to be water vapor that's transported by diffusion or air leakage. So this could move outward or inward depending on the conditions. Both interior and exterior conditions could be moving one way or the other. And then you've got number three here, built-in construction moisture. This is very near and dear to me. I live and work in the Pacific Northwest in Seattle. It rains a lot here, so when we build buildings, we tend to build in a lot of construction moisture. So we need to make sure we have a mechanism for that to dry out over time. And then the fourth is just groundwater. That can also get in and soak up into our building. So those are the sources of moisture. And then how we get rid of that moisture is again going to be four different ways. So we've got evaporation, right? That just occurs at the surfaces. We've got water vapor transported by diffusion. So again, depending on the environmental conditions, this could be moved diffusing outward or inward. And then drainage, which is where the Rainscreen really comes in, and ventilation, so drying by air exchange right through that cavity there. So we've got the number three and number four are really essential with Rainscreens. Okay, so we've got some examples here of different cavities. So air spaces, they can be created by a number of different methods, right? So that one example I showed was just vertical wood strapping or wood furring. We see this very often in multifamily buildings. Great way to get that Rainscreen. You've got that vertical cavity where water can drain through and airflow can get in behind the cladding. Commercial buildings typically see metal studs and more uh, fiberglass or composite materials here. We've got some looks like vertical girts or hat channels in this picture here that are creating that airspace. The cladding is going to go over top of it. We're also seeing quite a bit in the residential world of just dimple mats or drainage mesh products that can create that cavity space where the siding just gets installed right over the drain mat. So lots of different ways to do it, right? So just some examples here, right? We see this this looks like a vertical girt or hat channel of some kind creating that. We see sometimes this approach here, number two, with the horizontal hat channels. But you got to be careful with this, right? So this number two here, I show here as actually not a Rainscreen because this hat channel, this horizontal hat channel is going to stop water from draining through that cavity because we have that flat profile cladding. So number three uses again that same hat channel, but we've got a profiled cladding that can allow water and airflow to drain and ventilate around it. Or another option, there's plenty of companies that make things like a perforated hat track or some kind of perforated horizontal element that you can attach cladding to or through, that's going to also allow drainage and airflow. So the details really matter. Just because you have the cladding spaced away from the WRB does not necessarily mean you have a rain screen. You got to look at exactly how it's attaching and how the water and airflow is going to transport through there. This is another really critical thing is, a vented cavity versus a ventilated cavity. So you see here on the left, the flashing is actually pushed down snug against the cladding here. So it's going to restrict that airflow through the cavity there. Whereas on the right side, you actually see a little gap above and below the flashing, so you can get free airflow through this cavity. On the left here, this is sort of like, it would be like plugging a straw and taking it out of your drink. There's still going to be water held in there. It's kind of the same effect. You will get some airflow in that cavity, but it's greatly diminished by choking off the top there. So you really want that the vent openings in this rain screen to be top and bottom, um, to maximize the drying potential there. All right, so let's talk about gaps. So how big does the gap need to be? Really not very big. There have been lots of studies on this. Um, we don't actually need much of a gap at all to allow drainage. We do need a bigger gap to allow any kind of decent drying potential in terms of airflow. But there have been lots of tests done that show that a gap as small as even a 16th to an eighth of an inch will allow for some drainage, so liquid water could drain out of it. But you're not really going to get airflow. For that, you need a bigger gap, somewhere, around the neighborhood of a half inch. That's going to give you pretty decent airflow potential, assuming you don't have restrictions at the top or the bottom. And then a larger gap, 3/4 inch or more, that's where you really get full, really good airflow through the cavity. You actually don't really want to go much larger than 3/4 of an inch a lot of time, because then you might run into issues with fire spread. You don't want a really deep cavity that's concealed. So 3/4 of an inch, or I've seen sometimes just an inch is really the max there. But let's see if we can spot the airflow paths, right? So we've got that in between these vertical girts. That's going to be our airflow path. For brick, it's just going to be the gap in between the brick ties. That's going to be your airflow path, and then we want to make sure there's those weeps at the top and bottom, or weeps at the bottom and vents at the top, to allow airflow through behind the brick cavity. Here we've got some foam insulation that's screwed on with these battens, these vertical battens. And we've got our airflow path, or our drainage path, on the front face of the insulation there. You may get some limited drainage behind the insulation. We do see a membrane there, but not much in the way of airflow. It's going to be pretty tight against there. All right, so once you start thinking about where you might have restrictions on this rain screen ventilation cavity, there's a lot of them, right? So we got to think about the base of the wall here. How does air and water drain out of there? Think about the through wall flashings, the head flashings at windows, right? This parapet detail here. Where does the air flow through there? Lots of different ways where we can have these flashings block off airflow if we're not careful. So really important to maintain drainage and ventilation at all these details, not just at the assembly level. We got to make sure we're looking at all these details to make sure that drainage and ventilation path is maintained. Oh yeah, and then the top of the wall as well, underneath that eyebrow roof thing that sticks out there. All right, so let's talk about cladding. Okay, so it's the non-load bearing element. forms the exterior layer of the assembly. So lots of different examples of this. Any of them can work with Rainscreen, right? You could even make stucco Rainscreen, EIFS or Rainscreen, if you wanted to. Metal panels, brick, terracotta, wood, high pressure laminates, all sorts of different things. Um, so these are all going to have very different aesthetics. They also will often have different degrees of what I like to call openness. So really, how much water will they let in? Um, and then also how they're attached varies quite a bit. So we need to think about that in terms of designing our rain screen. Um, how are these actually going to attach? How are they going to be supported? Will that impact our cavity's ability to dry or drain? All right. And so a lot of these claddings, some of them will have much better water resistance than others, right? So things like lapped or well-jointed claddings actually let very, very little, almost no water actually gets through the cladding. It sheds water really well. Nearly 100% of the water just goes down the face of the cladding. You might get a little bit behind there at interface details, but not much. Um, so, airflow behind there will help remove anything that gets behind. But then you start to get into things like paneled claddings with joints that are either closed or sealed. They will let more water in um, at all these panel joints, but again, they'll hold out water fairly well. And then you get into things like open joint cladding or even perforated claddings. Those will let a lot of water into that rain screen cavity. So the degree of openness of the cladding will affect essentially all the other stuff behind it. So how much water are you really expecting in that cavity? That might impact things like which fasteners you use, especially if you're in a marine environment. How much corrosion resistance should those fasteners have? That could vary depending on how much water is going to get in there. Um, or your flashing details, how often you need kick-out flashings to get water out of that cavity. That might be impacted by the openness of your cladding system, or even what membrane you use. If you actually have an open joint or perforated cladding, you need a membrane that can handle UV exposure, permanent UV exposure through those gaps. And that brings me nicely into the next layer, the WRB. So this is the inner layer of the rain screen. So this is the inboard side of the cavity. It's most often going to be a membrane, but it's not always. There's lots of different ways to do this, right? We've got a picture here of spray foam that can actually work as a WRB. We also sometimes see just insulation, board insulation that is taped at all the seams. That can function as a WRB, but a lot of times it's going to be a membrane, either fluid applied or sheet applied membrane. Could be self-adhered, could be mechanically fastened. There's also lots of newer systems where it's integrated into the sheathing, and you just either tape or seal the joints. But it's going to resist water. This is the water resistant barrier is your last line of defense against water. So it's really defined as the layer in the wall where if you've got water behind that layer, it's a problem. Um, and so this is where all the water has to stop. Um, the backup wall structure. Again, rain screens can work with essentially any kind of backup wall structure. We've just got a few here. Your typical stick frame, wood frame building, mass timber works well with that. Steel studs, ICF, concrete, CMU, you name it. You can put a rain screen over it. So it's a really versatile way to design a wall. It's going to manage the water outside of your structure. All right. Now let's get into the additional components here. Um, so we've covered kind of the outer layer and the inner layer and the backup wall. but there's a lot of stuff in the middle. So there's quite often exterior insulation, continuous insulation. There's the cladding attachment system itself, so what holds the cladding on the building. Um, you may also have insulation within the backup wall. You may have another vapor control layer in there that's going to depend on climate, but lots of other stuff going on here. Um, so for the skinnier walls where cladding is attached basically through the rain screen cavity directly, just using long screws that go back to studs. Um, that's a bit simpler. So you can, this is showing hat channels or just a drainage mesh here. Um, that can work well. Um, Once you start adding exterior insulation, though, then you typically need something structural that spans through that insulation. And this is where this is quite common on commercial buildings to have continuous insulation requirements here. It depends on the climate zone, but in most climates, this is a requirement now. Um, so how do we actually do that in a way that doesn't compromise the insulation? So the old school approach is shown here, where we just have these continuous metal Z-girts that just punch through the insulation. This actually reduces the effectiveness of that insulation by a huge amount, 50% or sometimes more, depending on the spacing and all that. But we've come up with better ways to do this now that don't compromise the thermal performance of all that expensive insulation we just put there, right? So there's really endless different ways to do it. Um, these are kind of the old school approaches, uh, vertical Z-girt, horizontal Z-girt, or a double girt system here on the right that is a little better thermally, but pretty poor thermal performance for a lot of these, just because you have so much metal going through the insulation that's going to conduct heat. So now there's dozens, I haven't listed them all here, but lots of different ways to get a better thermal performance out of your continuous insulation. So there's clip and rail systems. There's continuous fiberglass girts. Basically just uh, different ways to have less metal going through your insulation. Lots of different ways to do it. Right? So clips and rails, they could be horizontal rails, vertical rails, um, all sorts of different types of clips. Um, but lots of different better ways to do that now. Um, the other benefit, which I don't think gets talked about enough, is if you've got this exterior insulation layer, it really helps with water control. And there's been some studies done on this with testing a bunch of mock-up assemblies with open joint cladding. But it turns out if you put a layer of insulation in front of your WRB, even with open joint cladding, most of the water just runs down the face of the insulation. There's actually very little water that ever touches the WRB. So it's adding that extra layer of protection. Um, you still need the WRB there because there still will be some water that makes it through the insulation at joints and around details and things like that. But um, it really protects everything from that moisture. So this is another big benefit of that extra layer is not just the thermal performance, but the added water control. You be a bit careful about exterior insulation. There's a lot of thought that needs to go into what type of insulation, how thick, all sorts of considerations like fire performance. Um, there's not a one-size-fits-all solution here, but lots of different ways to do it. I'm showing here some polyiso, some spray foam, some XPS, mineral fiber, all sorts of different products. They all have kind of different benefits and limitations. Um, so they can also affect the overall vapor permeability of your wall assembly. So if you're not careful, you can actually limit drying to the exterior here when you might need drying to the exterior. So one thing to be careful about if you're in certain climate zones, colder climates especially, what type of exterior insulation you're putting on the building. Right. So here we've got this is mineral fiber that's in between these vertical rails with looks like fiberglass clips supporting those rails. Right. This is a rigid foam. This is a polyiso with a foil facing. So this is going to be a higher R value per inch, but it's vapor impermeable. It's also quite water resistant as well. Or this is just spray foam in between these horizontal girts with clips behind them. So lots of different ways to do it. Again, going to be different depending on climate zone, fire requirements, how much R value you actually need, et cetera, et cetera. There's lots of different variables here between what type of exterior insulation you might need. Do need to talk about air barriers as well. This is another critical part of the enclosure. This is often actually one and the same as the WRB. So quite often these membranes will be serving multiple purposes. So a lot of them are a water-resistant barrier and an air barrier. They're designed to do both, so they will stop airflow and water. Some of them will also be vapor barriers, so they will stop three different things: vapor diffusion, airflow, and water. But the air barrier itself is what controls air moving through the building enclosure. So we we need them. They're code required. They also actually improve resistance to water intrusion by eliminating essentially a hole through the building. Um, so yeah, there's lots of other benefits as well. That's kind of a whole separate presentation, but they improve indoor air quality, reduce energy use, better acoustic performance, all sorts of benefits to having a good air barrier. Um, it's no matter what climate zone, it's always a good idea, and it's essentially always required by code now, both in IECC and ASHRAE. I think in every climate zone except for 2B, you have to have an air barrier, and they will help your building perform better. So they have to be continuous, and they can be put anywhere in the assembly. So there is actually often more than one airtight layer in the assembly. Quite often you'll see it as the WRB on the exterior sheathing, but sometimes it's going to be they'll tape up the face of the insulation. That's the air barrier. Sometimes it'll be inside. It could be a vapor control layer that's sealed up as well on the interior side of the wall. Doesn't matter. It's not climate specific. It just needs to be there and be continuous, which is not the case for the vapor retarder or vapor control layer. This actually does matter what climate you're in, where this goes, and how permeable or impermeable it can be. Um, I won't get into a ton of detail on this, but this is generally vapor control area needs to be on the warm side of the assembly. So if you're in a cold climate, that's going to be the interior. If you're in a hot climate, it's going to be the exterior. Um, if you're mixed, that gets more complicated. But this is not the same necessarily as the air barrier. These could be two different layers in the assembly. Um, so if you're like me and you just stare at buildings in construction all the time, I like to actually spot Rainscreen assemblies out in the wild when things are under construction. I don't know if anyone else does this too, but I like to get out there and see if I can identify where is the actual drainage layer, how's it going to dry out, is there enough of a cavity for airflow, are they blocking it anywhere? This is a fun activity I like to do when I'm just out around a new city or even in my own city. Um, so yeah, just summarizing this rain screen wall, we've got this exterior assembly applied to an exterior wall. We've got our outer layer, got our inner layer, got the cavity in between that needs to be sufficient for the passive removal of liquid water and water vapor. Tons of different ways to do it. We didn't even talk about things like glazing systems that are rain screens, but that's a big part of it as well. Things like curtain walls and window walls that actually have water management in a rain screen form. They're intended to drain and dry out. But this is really it's an essential part of a high performing building. So it's the most effective way to manage rainwater. Um, it's going to increase a building's durability and resilience. It allows you the opportunity to add more insulation, and make the building more energy efficient. We're seeing a lot of really cool deep energy retrofit projects that include adding a rain screen and insulation to an existing building. That's going to be a really important thing to improve our existing building stock in the future. Um, Rainscreen is, it's a whole assembly. It's not any one particular system. So it's something that really needs to be designed holistically, thinking about not just the cladding, not just the cladding support, but the whole system. So what's the backup wall? What's the insulation strategy? What's the WRB? Think about it holistically, because there are knock-on effects to changing one part and not thinking about the whole system. Um, it leads to safer and healthier buildings, and gives you that design freedom, and versatility. It really doesn't limit your design choices. You can really make any kind of material into a rain screen if you wanted to. Lots of different products and materials available, that can be used effectively in a rain screen. And we do have some really great information on RAiNA's website. We've got technical bulletins and industry articles and resources and things like that. So please feel free to check out our website. Also want to remind everybody that RAiNA is having our annual conference in Philadelphia. I believe it's November 5th. There's information on how to sign up for that. We've got some really great speakers lined up, to talk about all sorts of different really interesting topics. You can go over to the rainscreenassociation.org to find out more information about that. And it looks like I talked really fast. So that's the end of the slides. Happy to get into questions now. Um, let's
Yeah, that's
see.
okay. We have quite a few questions, so that's
Great.
perfect. All right. So first, I'll start with we have a couple people asking for a copy of the presentation.
Great.
So
Yeah.
can you clarify that you'll be sending that afterwards to folks who
Yeah,
ask?
so we'll get a list of the all the questions. So if you ask for a copy in the presentation, or in the question and answer window, we can follow up with you individually and send you a PDF copy.
All right. Yeah, that's great. Thank you.
And then I know you're recording this, Kayla, but is there somewhere that you're gonna post the recording as
Yes,
well? Okay,
definitely. We'll have
great.
that on our webinar page on
Okay.
Acelab and probably by the end of the day today. So
Mhm.
we'll also send you
Yeah,
all a copy of the recording as well over
cool.
email.
Yeah.
Yeah, awesome. So next question we have is how are rain screens implemented with stucco and EIFs and cladding
Yeah.
systems? Sorry. Yeah.
Uh, Well, you basically just have to add a drainage cavity. So with stucco, a lot of times that's just added. It's with a drainage mat, that then the some well there are, yeah, I can't get manufacturer specific. There are some drainage mats that actually have a lath built into them that you can stucco onto. Sometimes you can just put a drainage mat there and then nail a lath over it. It's really similar with EIFs. You can add a drainage mat and then put the insulation over that, and just add that drainage cavity in there. and you're good to go. Just make sure all your openings, everything's flashed properly to allow that water to drain out.
For sure. Yeah, that makes sense. Wonderful. All right. Next question. Can you talk more about the compliance with NFPA 285?
Um, well, uh, so NFPA 285, that's maybe a whole other presentation, I guess. Um, it yeah, that's an assembly test that looks at fire spread vertically up through an assembly. Um, I will say there are lots of Rainscreen assemblies that have been tested and can meet NFPA 285, but that it depends on the whole assembly, everything. So, not just the backup wall, like the cladding matters, the cladding attachment matters, the type of membrane matters, um, the type of insulation matters. So yeah, it's a very expensive test to run. It is not a requirement for low-rise buildings. It's yeah, I guess I don't know how much I could maybe answer some more specific questions about NFPA 285, but it is something that we do need to deal with. But that shouldn't be a limiting factor. Having a rain screen, there are lots and lots of rain screen assemblies that can meet 285.
Yes, absolutely. That makes sense. All right. Next question. What is the maximum vertical spacing of flashing with drip edge in exterior metal cladding?
Uh, there isn't necessarily a maximum. Um, it's I guess that it's going to depend on a lot of things. So how the cladding is actually accommodating movement matters, and that's going to be very specific to a type of cladding system. Um, I guess, well, that's really just more where the panel breaks need to go. But uh, you don't really need any, like it's good practice to have flashing at all those panel breaks where there's a movement joint. That's not a requirement, but it is good practice to manage the water in that way. Um, yeah, there's not a maximum vertical spacing. Um, yeah, for the flashing.
Okay, great. All right. Next question. How are screw penetrations from hat channels or clips handled? Seems like they would create an opportunity for water damage when they are puncturing the WRB.
Uh, yeah, I mean they do, but it's well, this is the benefit of the rain screen is that there's really not a ton of water that ever touches those penetrations in the first place because it's all drained and handled in front of that. But yes, it's I guess I don't want to overstate or understate the importance of this, but it's a lot of times not really that big of a deal. A lot of membranes actually will somewhat self-seal around screw penetrations. If you get enough water on those penetrations for a long enough period of time and get a pressure to drive water through, you will see them leak for sure. But you have to have the right conditions and the right exposure for that to happen. This is kind of where a lot of the nuance in rain screen design comes in, like the system that you would design for, let's say, a 4-story building with big overhangs around the roof versus 40-story high-rise building with open joint cladding. Those two scenarios are very different in terms of rain exposure. And so you would need to account for that. So that, in some scenarios, depending on how exposed the wall is, how much rain load you're really going to see on that cladding, how open the cladding is, how well is the cladding going to shed water. you may want to do things to enhance the cladding attachment detailing. And by enhance, I really just mean like, drive the screws through wet sealant, right? Or something like that, where you're enhancing the penetration detailing to minimize the risk of water getting through the WRB at those fasteners. But in a lot of cases, the exposure is just not that extreme. Like we're not building submarines, so if you put enough water and enough pressure on anything, you can get it to leak. But um, it's you need to be realistic about how much water it's going to be exposed to.
Absolutely. Thank you. All right. And we've got lots of questions coming in, so we probably won't have time for all of them, but
Sure, yeah,
um,
and I'll get a copy of these questions. So anything we don't get to,
yeah.
I could follow up with you individually. I think we should have your email
Yeah.
from this if you registered. So yeah,
Yes,
what's next?
definitely. Yes, let's get a few more in here. Next question is, can you explain AB and VB, also in cold and warm climates, locations of the two?
Yeah. So air barrier and vapor barrier are two different things, and uh, there's a lot of confusion about this because they're quite often one and the same in a lot of building designs. But they it's two different functions. So a vapor barrier, uh, it limits the flow of water vapor by diffusion. So diffusion happens when you've got a higher concentration of water vapor on one side of a wall versus the other. Everything always tries to equalize out, so you will get vapor drive or vapor pressure, which actually diffuses vapor through that assembly. So it'll go from a higher concentration to a lower concentration. And so the rate of diffusion depends on the permeability of that membrane that it's going through, or really the whole assembly. Um, so the air barrier stops airflow, but the tricky part is that there's a lot of water vapor that is contained within the air. And so it also stops the flow of vapor, but by a convective method. So it stops the actual air movement. So you can have vapor permeable membranes that are airtight that will stop airflow, but they will still allow for diffusion. Um, so this is like, really any house wrap is going to be like this. There's a lot of different products that count as this. So the air barrier, if it's vapor permeable, can go on any side of the wall, doesn't matter. The vapor barrier really needs to go on the warm side of the wall. And so in a cold climate, it's going to be on the interior side of the wall. On a warm, hot, humid climate, it's going to be on the exterior. Um, so uh, yeah, I guess hopefully that explains it. So in mixed climates, it gets a little tricky. Sometimes you'll actually have a semi-permeable vapor barrier. So it's not actually a vapor barrier, and I should be careful and use the correct terminology. It's a vapor retarder, so it slows down vapor diffusion. It does not stop it. So it does allow for some drying in either direction. So these are the kind of things you tend to use in mixed climates, where it's semi permeable or semi impermeable. It depends on the climate zone, depends on the insulation configuration, but that can get more complicated. Yeah, I guess I would need specifics to to get into more details here, but I hopefully answered that question.
Yeah, I think so. All right. What is the most commonly missed detail that makes a huge difference in performance?
Oh, in terms of rain screens, it's I would say generally just uh, some way of blocking airflow or drainage that people didn't intend. something that traps water that no one really considered because they're not, maybe they're not thinking in 3 dimensions. They're kind of just looking at 2-dimensional details on the page and not fully understanding how different parts and pieces come together.
Gotcha. All right. Next, it looks like somebody's looking for more information about the moisture intrusion from the inside.
Um, I'm not quite sure what they mean. Maybe like uh, I'm not sure what that means. Like plumbing leaks or internal water sources or
Yeah, that's
uh,
okay. We can try to
yeah.
get more information.
Um, or maybe just really high humidity interior environments. Like an indoor pool.
Mm,
That can cause all sorts of problems. That's more, I would say, related to air leakage and diffusion than that's that's kind of a different set of problems that we're trying to solve um, than the rain screen itself. Um, you don't want air leakage in those types of occupancies. Air barriers are really important because we want to essentially remove all that interior moisture through the ventilation system. Any natatorium is going to have some huge exhaust extraction system um, to manage humidity levels, and then you just really want to keep the moist interior air away from the colder parts of the wall. You don't want it to condense anywhere. Um, I don't know if I really understood that question, but hopefully
mm.
that answers it.
Yeah, I think so. All right. Next we have other than the use of continuous insulation and the use of air barrier rather than damp proofing, how does the definition of the system vary from how we have been doing it for the last 50 years?
Well, I think you nailed it in that question there. I think that the use of an air barrier is a newer thing, and uh, yeah, but rain screens are not a new concept. That is correct. So there have been references to drained or back ventilated systems for the better part of 50 or even more years. They haven't been as widespread as I'd like them to be, but it's certainly not a concept that was just invented. But the idea of having an airtight layer on the interior side of it um, is a newer concept, and that really does help to manage water penetration as well, just having that all sealed up. Um, so that's, I would say, a big difference in the last 50 years is the incorporation of air barriers and that continuous insulation as well. That's a relatively newer concept. We didn't really used to be concerned about thermal performance whatsoever.
Hmm. Yeah, okay. I think we have time for maybe one more question. Let's see. With continuous exterior rigid insulation, is there a different insulation application or are the fasteners just longer for the attachment?
Um, this might be referring to a photo I had of the vertical wood strapping over the foam insulation. That's just with long screws. That's all it is. Just really long screws that go all the way through the insulation, through the sheathing, into the studs. You do have to line up where the studs are and have all that layout figured out beforehand, which is a little bit tricky, but that is certainly doable. And that's all we're doing. For some of the clip systems that I showed, the clip and rail systems, the fasteners would just go through the clips, and then you would have just other, those would be kind of normal length, and then you'd have other fasteners that go through the rails that attach the cladding to the rails. So you're not really using long fasteners there.
Gotcha. Awesome. Well, I think we're right at time.
Okay.
So yeah, thank you everyone for the great questions. We'll follow up with you afterwards to get answers to anybody we didn't have time for. But Denali, is there any final comments you'd like to make before we wrap it up?
Don't think so. It looks like, yeah, there's a few other questions that I can follow up with individually and send out the copy of the presentation. But thanks everybody for coming and hope it was informative.
Yes, thank you. Thank you, everyone. Have a great day. Bye.
Yeah.